Hello. In this lecture, we'll continue our discussion of the Bitcoin cryptocurrency. Uh, so recall that mining is the process by which new blocks are added to the blockchain. Uh, so this figure shows the blockchain. This is the very first block known as the Genesis block or block 0. Then this is block 1 and so on. This is block n, which is the latest block in the blockchain. Each block consists of a block header, which is shown here, followed by a list of transactions. So these transactions are shown over here. So these transactions are of two types. The first transaction in every block is a special transaction called the Coinbase transaction, and the other transactions are known as regular transactions. So the first transaction, that is the Coinbase transaction, it encodes the transfer of the block reward to the miner which added the block to the blockchain. Recall that we discussed that the block reward consists of the block subsidy plus the transaction fees from the other transactions. That's the block reward of a block. It consists of the block subsidy, which is a constant number of bitcoins, for example 12.5 bitcoins, plus the transaction fees from the regular transactions in the block. So this Coinbase transaction encodes the transfer of the block reward to the miner which added the block to the blockchain. So each Coinbase transaction involves the creation of new bitcoins. For example, 12.5 bitcoins may be created, and the Coinbase transaction encodes the creation of these bitcoins. The other transactions in this list are called regular transactions. So in summary, there is one Coinbase transaction in every block, and there are 0 or more other transactions known as regular transactions. So these regular transactions encode the transfer of bitcoins which were created in some previous block. For example, initially Alice may have created a block and she earned some bitcoins, some new bitcoins. Later on, Alice paid some of these bitcoins to Bob. So later on, in another block, a transaction was added which encoded the transfer of these bitcoins from Alice to Bob. So such a transfer of bitcoins which were created in some previous block are encoded in regular transactions. A block must contain exactly one Coinbase transaction, but it may contain 0 or more regular transactions. Typically, it contains several regular transactions, and these regular transactions are a source of revenue apart from the block subsidy for the miner who mines the block. Nodes that want to record new regular transactions in the blockchain broadcast them on the Bitcoin network. So these transmissions of new regular transactions are received by miner nodes, and when they create new blocks, they may include these transactions in the blocks that they add to the blockchain. So when other nodes hear these new transactions, they add them to a transaction memory pool. It's called mempool, and it is stored in the local memory of the miner node. Each miner node receives these transmissions of new regular transactions from other nodes in the network, and they add them in this transaction memory pool called mempool. A miner node forms a candidate block by collecting some transactions from its mempool. So recall that the size of a block is 4 MB. The miner node collects enough transactions so that these transactions will roughly fit into 4 MB, leaving space for the Coinbase transaction and the block header. So the miner node forms a candidate block by collecting some transactions from its mempool, and it includes a Coinbase transaction in the candidate block, which transfers the block reward to its own Bitcoin address. And apart from this, the miner node adds the header to the candidate block. So the block consists of these entities. One is the regular transactions from the mempool, the other entity is the Coinbase transaction, and the third is the block header. At any time, there will be several miner nodes competing to add the next block in the blockchain and claim the resulting block reward. Whichever miner node is the first one to generate a correct block, that miner node adds the block to the blockchain. the candidate blocks created by these different minor nodes will differ in the Coinbase transaction. For example, consider candidate blocks created by 3 different miners, say A, B, and C. The candidate block that is created by A, in that candidate block, the Coinbase transaction will say that the block reward is transferred to A. Similarly, in the candidate block that is created by B, the Coinbase transaction will say that the block reward is transferred to miner B. And in the candidate block of miner C, the Coinbase transaction will say that the block reward is transferred to miner C. So these candidate blocks created by these different miner nodes A, B, and C, they definitely differ in the Coinbase transaction. These candidate blocks may also differ in the regular transactions that are included in them, because different miner nodes may have different sets of transactions in their respective mempools. How can it happen that different miner nodes have different sets of transactions in the mempools? Recall that nodes that want to record new regular transactions, they broadcast them on the Bitcoin network. So all the miner nodes eventually receive all the regular transactions that are broadcasted on the Bitcoin network. But this can still happen. That is, different candidate blocks can still differ in the regular transactions included in them. And that happens because the miner nodes receiving transactions broadcasted on the Bitcoin network at different times due to network latencies. Consider a particular node, say D. This node D broadcasts a regular transaction which it wants to include in the blockchain. A is nearest to the node D, so A receives this regular transaction first. B and C receive this regular transaction after some latency. So in the candidate block of A, this transaction, regular transaction sent by node D is included, but in the candidate blocks of B and C, this regular transaction is not included because it was received by B and C after some latency. So that's how it can happen that the set of regular transactions included in the candidate block of one node differs from the set of regular transactions in the candidate blocks of the other nodes. Now we discussed the different fields in the block header. We discussed the end time field. The height of a block in the blockchain is the number of blocks preceding it in the chain. So in particular, the Genesis block has height 0 because there are 0 blocks preceding it. The immediate successor of the Genesis block has height 1 and so on and so forth. So recall the block header structure which we discussed earlier. It contains all these fields, and recall that the fields, the 4-byte fields which have n at the beginning of the 4-byte fields, so these are integers. And these two fields, hash previous block and hash Merkle root, these are cryptographic hash function values, and they are 32 bytes in length. So this end time field, which is 4 bytes in length in the block header, is populated with the timestamp in Unix time format to record the time of the block creation. At the time when the block is created, so the corresponding timestamp is put into the end time field in the block header. It is in Unix time format. What is Unix time format? Unix time is the number of seconds which have elapsed since 12 a.m. UTC on January 1st, 1970. So UTC is Coordinated Universal Time. Unix time is the number of seconds which have elapsed since this time instant. So hence it is an integer, and this integer is recorded in the end time field in the block header. So each node in the Bitcoin network has a local clock which is not necessarily synchronized with the local clocks of other nodes. So recall that the Bitcoin network is a peer-to-peer network, and in a network in general, the local clocks of different nodes are not synchronized. That's because of typically because of clock drifts. For example, consider two nodes A and B. Initially, their local clocks may be synchronized, but the crystals at the two nodes which maintain time, they may drift with time, or they may have slightly different frequencies. For example, one node may have a clock which runs at the speed of 10 megahertz. Another may have a crystal which runs at 10.00001 megahertz. So because of such differences in the frequencies of the crystals which maintain time, and the drifts in these frequencies of these crystals. So hence different nodes don't have always synchronized clocks. So hence the local clock of a node in the Bitcoin network may not be synchronized with the local clocks of the other nodes. So there is no globally unique notion of time in the network. As an example, if the local clock in one Bitcoin network is 4 p.m. on a certain date, then the local clock in another node may be 4:01 p.m. on the same day, and the local clock of another node may be 3:59 p.m. on the same day, and so on and so forth. The Bitcoin system does not specify an explicit algorithm for calculating the end time field in a candidate block, but it specifies a lower bound and an upper bound on the end time. So we'll specify what these lower bound and upper bound are. The Bitcoin system imposes the following two constraints to ensure that the timestamp in the end time field is approximately correct. So out of these constraints, one is a lower bound on end time and the other is an upper bound on end time. So the first constraint is this: in a candidate block at height n, the end time field should be strictly greater than the median of the end time values in the 11 blocks in the blockchain at heights n-1, n-2 up to n-11. So consider the previous 11 blocks in the blockchain and find the median of their end time values. The end time field in the current block should be strictly greater than this median. So this says that the timestamps in different blocks are roughly in an increasing order, but they may not be strictly in an increasing order, because this end time field in the current block is only required to be greater than the median of the end time values in the 11 blocks at these heights. So hence the end time values are not strictly in increasing order. So this is the other constraint. When a network node receives a candidate block created by a miner, it rejects the block if the end time field specifies a time which exceeds the node's network adjusted time by more than 2 hours. What is the network adjusted time of a node? The network adjusted time at a node is the median of the local clocks of the other nodes it is connected to. For example, consider a node A in the blockchain network. Suppose it is connected to these other nodes B, C, D, E, and F. We can find the median of the local clocks of these other nodes. For example, B has a local clock of TB, then C has a local clock of TC, D has a local clock of TD, and so on and so forth. F has a local clock of TF. So the neighbors of node A are these B, C, D, E, F. And their corresponding local clock values are TB, TC, TD, TE, and TF. We find the median of these 5 values: TB, TC, TD, TE, and TF, and that is the network adjusted time of node A. A miner node is free to set the end time field to any value which satisfies these above constraints. So this is the constraint which specifies the lower bound on the end time field, and this constraint specifies an upper bound on the end time field. Between this lower bound and upper bound, any value is valid. So the miner node can set the end time field to any value which satisfies these constraints. So this first constraint specifies a lower bound on end time, and it can be calculated from the current blocks in the blockchain. So the miner node has to just look at the previous 11 blocks in the blockchain and read their end time values and find the median. And then the miner node has to just ensure that end time field in the current block has to be some value that is greater than that median value which it has just calculated. But this upper bound specified by the second constraint cannot be explicitly calculated by the miner, because it does not know the network adjusted times at all the other nodes in the network. For example, consider this node A. It does not know the network adjusted time at node E, because it does not know the set of neighbors of node E, their local clock values, and so on and so forth. So hence this upper bound cannot be explicitly calculated by a miner node. But the minor node can hope to satisfy this upper bound with high probability by using n time values that are equal or close to its own network adjusted time. So typically in practice, the local clocks of different nodes are at least loosely synchronized. For example, if the local clock value at a particular node is 4 p.m., then the local clocks of other nodes are close to 4 p.m. Hence, a minor node can use n time values that are equal or close to its own network adjusted time, and this calculated network adjusted time, that is its own network adjusted time, will be likely close to the network adjusted times of the other nodes, that is its neighboring nodes. So hence, by using this process, the minor node can hope to satisfy this second constraint. And also, we should notice that there is an interval of 2 hours which is specified here. So when a network node receives a candidate block, it rejects it only if it specifies a time which exceeds the node's network adjusted time by more than 2 hours. So the possibility of the local clocks of different nodes being away from each other by more than 2 hours is it's quite unlikely. So hence, typically this n time field satisfies these constraints. Fine. So we have discussed the n time field in the block header. Now let's go back to the block header. We now discuss this n bits field in the block header. It specifies a target which is related to the hard problem that a minor node must solve in order to successfully add a block. So this n bits field in the block header, it encodes a 256-bit unsigned integer called the target threshold using base 256 scientific notation. Recall that the n bits field is 4 bytes in length. Let b1, b2, b3 and b4 be the 4 bytes of n bits. So in this scientific notation, b1 is the exponent and b2, b3 and b4 are the mantissa. So that is 256-bit unsigned integer that is represented by these 4 bytes is given by the following. The target threshold corresponding to the n bits value is t equals b2, b3, b4 into 256 to the power b1 minus 3. So we can see that b1 appears in the exponent and b2, b3, b4 are the mantissa. So the target threshold is mantissa multiplied by 256 to the power exponent, that is b1 minus 3. So here b1, b2, b3, b4 are interpreted as unsigned integers. So some examples are given in this table. For example, suppose the n bits field is this, b1 is 0, 3, b2 is 1, 2, b3 is 3, 4 and b4 is 5, 6. Then the mantissa is b2, b3, b4, which is this 1, 2, 3, 4, 5, 6, and b1 minus 3 is 0 because b1 is 0, 3, so b1 minus 3 is 0. So hence 256 power 0, that means no shift. So hence the target threshold is simply this 0x 1, 2, 3, 4, 5, 6. Now consider another example where b1, b2, b3, b4 are as in this field. So b1 is 2, so b1 minus 3 is minus 1. So this 256 power minus 1, we have the exponent is minus 1. So hence we have b2, b3, b4 multiplied by 256 to the power minus 1, which corresponds to a shift to the left by 1 byte. So hence we take this value 1, 2, 3, 4, 5, 6 and shift it to the left by 1 byte. That gives us 1, 2, 3, 4. So hence the mantissa is 1, 2, 3, 4. So the target threshold is 1, 2, 3, 4 in hex. Similarly, in this case, b1 is 5, so b1 minus 3 is 2. So that corresponds to 256 to the power 2. That is a shift to the right by 2 bytes. Hence, the corresponding value of the target threshold is this in hex 1, 2, 3, 4, 5, 6, 0, 0, 0, 0. 256 to the power 2, that means we have shifted to the right by 2 bytes and so on and so forth. So these are some example values of n bits and the corresponding target threshold that is encoded by them. The maximum value of b1 is 32. This ensures that the target threshold t can be represented by a 256-bit string. So the maximum value of B1 is 32. So the maximum value of B1 minus 3 is 29. So we have some values B2, B3, B4, and the exponent is 29. So that means shift to the right by 29 bytes. So that corresponds to a 32 byte value. So 32 bytes is 256 bits. Hence, T can be represented by a 256 bit string. So the maximum value of B1 is 32. So what is the reason for ensuring that T can be represented by a 256 bit string? The reason is that this target threshold T is compared with the double SHA-256 hash of a block header. And recall that the output of an SHA-256 hash, as the name suggests, that is a 256 bit string. So since T is compared with the double SHA-256 hash of a certain block header, T is restricted to be a 256 bit string. Now the target threshold T is a network wide setting which is adjusted by all the network nodes every 2016 blocks. So we'll discuss how the target threshold is adjusted by the network nodes. So we now discuss how to find a valid block. So the goal of a miner is to find a candidate block such that the double SHA-256 hash of its block header is less than or equal to T. So recall that in order to mine a new block, a miner has to solve a difficult problem, and this is that difficult problem that the miner has to solve. The miner has to find a candidate block such that its double SHA-256 hash of the block header is less than or equal to T. Now in the block header there is the n-nonce field which we discussed earlier. So if we go back to the header of the block, then recall that one of the fields is the n-nonce field which is 4 bytes in length. So the miner is free to set this n-nonce field in the header which is 4 bytes in length to any value to achieve this goal. So since the n-nonce field is 4 bytes in length, 4 bytes is 32 bits. So there are 2 to the power 32 possibilities for setting the n-nonce field. The miner has to try out different possibilities of n-nonce values until it gets a candidate block such that the double SHA-256 hash of the block header is less than or equal to T. So how does the miner find such a block? It is computationally, recall that it is computationally hard to find the pre-image of a given hash value. So hence the miner has to try out different n-nonce values until the double SHA-256 hash of its block header comes out to be less than or equal to T. So for example, recall that the miner initially creates a candidate block by putting some regular transactions and the Coinbase transaction and a block header. So first it tries by setting n-nonce equals 0, for example, and finds out the SHA-256 hash of the block header. If it is less than or equal to T, then the miner is done. It has found a block whose double SHA-256 hash of the block header is less than or equal to T. If not, then it tries with the next value, that is n-nonce equals 1, for example, and then checks whether the double SHA-256 hash of its block header is less than or equal to T, and so on and so forth. Then it tries n-nonce equals 3, and then n-nonce equals 4, and so on and so forth. So it tries different values of n-nonce until it gets a block for which the double SHA-256 hash of its block header is less than or equal to T. Now the probability that for a given n-nonce value, the double SHA-256 hash of its block header comes out to be less than or equal to T is this T plus 1 upon 2 to the power 256. So this is the required probability. And that is because recall that the output of a cryptographic hash function can be assumed to take any value equally uniformly at random among the 2 to the power 256 possible values. So there are 2 to the power 256 possible output values of the double SHA-256 hash, and out of these the hash is less than or equal to T in T plus 1 of the values, that is 0, 1 up to T. So hence the probability is T plus 1 upon 2 to the power 256. The probability that for a given n-nonce value, the double SHA-256 hash is less than or equal to T. Now, what is the average number of trials required until success? The claim is that the average number of trials is required until success is 1 by p. So let x be the number of trials required until success. So x is an integer, it is a positive integer, which is a number of trials required until success. So in each trial there is a success with probability p. So x equals 1 if the first trial results in success. So x equals 1 with probability p. And x equals 2 if the first trial results in failure, which happens with probability 1 minus p, and the second trial results in success, which happens with probability p. Similarly, x is 3 if the first two trials result in failure and the third trial results in success, which happens with probability 1 minus p squared into p. X is 4 with probability 1 minus p cube into p, and so on and so forth. So what is this distribution? This is a geometric distribution. So x is a geometric random variable. So the success probability of x is p. So there is a standard result that if we have a geometric random variable with success probability p, then its expectation is 1 by p. So in this case, we have that expectation of x is 1 by p. So from this fact, it follows that the average number of trials required until success is 1 by p. Here's an example. The value of the n bits field on Jan 1st, 2017 was this in hex 180375FF. The average number of trials until success was approximately 2 to the power 70. If you compute this, it comes out to be 10 to the power 21. Now, since a large number of trials are required until success, that is the reason why mining is a computationally hard problem. So, on average, one has to try at this time, that is Jan 1st, 2017, one had to try approximately 10 to the power 21 different values until one got a value which corresponded to success. A miner which successfully finds a block such that the double SHA-256 hash of its block header comes out to be less than or equal to T is said to have found or mined a valid block. Now, what are the actions taken after finding a valid block? So, what does the miner do after it finds a valid block at height T? So, it immediately broadcasts the block on the Bitcoin network. And then the miner appends the block to its local copy of the blockchain and it begins mining for the next block at height n plus 1. So, since the miner has successfully found a valid block at height n, it has got the block reward for this particular block, then it broadcasts the block on the Bitcoin network so that the other nodes know that a block has been successfully mined and they add that block to the blockchain, to their local copy of the blockchain. And then this node appends the block to its local copy and begins mining for the next block at height n plus 1. Initially assume that all the other nodes have the same copy of the blockchain consisting of blocks from the genesis block to a block of height n minus 1. When the new block at height n arrives at one of the other nodes, the recipient node, which was still mining for a block at height n, stops mining and it appends the new block which it just received to its local copy of the blockchain. And then it starts mining for the next block at height n plus 1. So these are the actions taken by a miner which receives a new block at height n. It stops mining and appends the new block to its local copy of the blockchain and starts mining for the next block, which is at height n plus 1. Now let's discuss typical double SHA-256 hash computation rates. The rate at which a computing device can calculate the double SHA-256 hashes of block headers is measured in these units. mega hashes per second or giga hashes per second or tera hashes per second. Now the rate of a typical PC is less than 100 mega hashes per second. In that example that we discussed earlier, one needed to calculate 2 to the power 70 double SHA-256 hashes on average for success. So to calculate 2 to the power 70 double SHA-256 hashes, a PC that operates at 100 mega hashes per second will require more than 300,000 years. So it is practically impossible for a PC to have a high probability of getting a success. Nowadays, mining is done using application-specific integrated circuits that are specifically designed to compute several instances of the double SHA-256 function in parallel, so that it's likely that out of these parallelly computed hash values, at least one of them will be less than or equal to t after several instances of the computation. Mining rigs which combine several such ASICs are available in the market, and they can deliver hash rates of the order of a few terahashes per second. A single mining rig that operates at 1 terahash per second will still require more than 30 years to calculate 2 to the power 70 double SHA-256 hashes of block headers. Hence, a single mining rig also, it's unlikely that a single mining rig will succeed in finding a valid block in reasonable time. Mining is typically performed by companies which have consolidated thousands of such mining rigs into data centers. If we add up the hash computing capabilities of all these mining rigs in parallel, then it comes out to be a large value. So now let us discuss how the target threshold T, which is encoded in n bits, is chosen. The Bitcoin protocol specifies that the average time required to mine a valid block should be 10 minutes. So how can the target threshold T be chosen to achieve this target? So one rule is that the target threshold T is updated once every 2016 blocks by all the nodes in the Bitcoin network. In particular, each time a node starts mining for a candidate block whose height is a multiple of 2016, then it updates the value of the target threshold T. So why is this value 2016 chosen? This 2016 is the number of blocks which would be found in 2 weeks if a block was found every 10 minutes. That is, 2016 is this 14 days in 2 weeks multiplied by 24 hours per day multiplied by 6. That is, since a block is found every 10 minutes, so there are 6 blocks found in 1 hour. That is how we get this value 2016. The time which was spent in finding the previous 2016 blocks is estimated by taking the difference of the end-time fields of the blocks whose heights differ by 2016. So we can consider the end-time field in the latest block and the block which is 2016 blocks previously. So we can take the difference of the end-time fields in these blocks, and thereby we can obtain the time which was spent in finding the previous 2016 blocks. Recall that the average number of trials required to find a valid block is 2 to the power 256 divided by t plus 1. Hence, the amount of time required to find a valid block is inversely proportional to t. And that is quite consistent with intuition. The larger the t, it becomes easier to find a block whose block header hashes to some value less than or equal to t. So this fact is important, that the time required to find a valid block is inversely proportional to t. The update formula for finding the new value t new from the old value t old is given by this expression, by this equation. T new is t old multiplied by measured duration for finding 2016 blocks in seconds divided by 2016 into 600. We now explain this formula. So recall that we want that the next block should be mined in roughly 10 minutes. Now 10 minutes corresponds to this. The duration for finding the next block is 10 minutes, which is 600 seconds. For finding the next 2016 blocks, the duration that we want is 2016 multiplied by 600. And from the previous blocks, we can look up the measured duration for finding 2016 blocks in seconds. Now we know that the duration is inversely proportional to the value t. From this formula, we can see that. So we have a simple inverse proportion problem. So t old corresponds to this measured duration, which is in the numerator of this formula. So this t old corresponds to this measured duration, and t new corresponds to 2016 into 600, which is what we want it to be. So hence, since t is inversely proportional to the duration, hence we get this formula. T new is t old multiplied by measured duration for finding 2016 blocks in seconds divided by 2016 into 600. So by setting the target to this value, we'll ensure that on average 10 minutes will be required for finding the next block. We ensure that for finding the next 2016 blocks, approximately 2016 into 10 minutes will be required. So this is how the threshold t is adjusted. So in summary, we discussed more information about the Bitcoin network. So we discussed several of the fields. We discussed how end time is set in the Bitcoin network, and we discussed how the threshold is set, and we discussed several aspects of mining. We'll continue our discussion of Bitcoin in the next lecture. Thank you.